This lecture is about nuclear emulsion. It will be arranged as usual in 3 modules. At the end of each module you will find a few simple questions just to check that you have got the main messages of the modules, and then at the end of the 3rd module there will be also a couple of homeworks. So nuclear emulsion is the oldest particle detector with an unsurpassed accuracy and with very innovative readout technologies. So in these slides I just give you the features of 2 kinds of nuclear emulsions. In general, nuclear emulsions are very similar to photographic films, so they are made of silver halide, typically silver bromine. So if you see the chemical composition, it is largely dominated in mass by silver and bromine, and there are lighter elements because these crystals, they are dispersed in an organic gelatin, and so here it comes the carbon, nitrogen and oxygen, and there's a small fraction of hydrogen. And you see on the left the composition of the opera film. Opera is the largest ever built emulsion detector. And on the right you see the modern emulsion film, which is called a nanoimaging tracker, which is used for nanometric application of the emulsion technology. And you see there anyway, I mean, for the need for these nanoimaging trackers, I mean, the silver and bromine mass fraction is even higher than the other. And then there are in the center bottom part of this slide you see the typical definition of the linear density of crystals, and also how this linear density is somehow related to the volume occupancy and crystal radius. Let me first say what is the main difference with respect to photographic films. Indeed, the main difference is that the ratio of silver halide to gelatin is up to 10 times larger than in photographic film. So this corresponds to a higher sensitivity. Then nuclear emulsions are thicker, from 10 to 100 times thicker, so this gives you a 3-dimensional reconstruction, not just the 2D reconstruction that you see with standard photographic films. And developed silver grains are smaller and more uniform, so well, uniformity goes to the and the smaller size of the crystals goes to a better stability and also to a better resolution of this device. What is the detection principle? So nuclear emulsion is basically like a semiconductor. So there is a valence and a conduction band, and the band gap is about 2.6 electron volt. So when a charged particle passes through, there is an energy deposition due to the ionization, which produce electron hole pairs. So there are lattice defects on the surface of the silver bromine crystal. These lattice defects, they act as electron traps, so they attract the electrons from the electron hole which are created, and these electron traps, they in turn attract the silver ions, which become silver atoms, and then aggregates of silver atoms produce the so-called latent image. So there is a chemical amplification of the signal later on, done with the chemical development of the film, which turns this latent image into silver filaments with an amplification which is from 10 to 100 million times. And then at the end you dissolve the crystal in the bath and you see this silver filament as a cluster made of several above threshold pixels when you take an image with a sensor of an optical microscopes. So again, this is the image of the valence band, the conduction band, the electron hole which is created, the electron traps, and then electron and silver ions. They get silver atoms, and then you have several of these processes going on. When you have at least 4 silver atoms put together, then this is according to the standard photographic theory, this is produce a latent image. And this is what you can actually see with an electron microscope. This is an opera film which was exposed to alpha rays, and then you see the image at the optical microscope. So there are hundreds of silver clusters per crystal. Then after the development process, then you end up with silver grains along the track, and then you have you see these silver light grains with typical size of a couple of 100 micron for the opera film. And so along, this is the number of grains which are produced by high energy pion in an opera films are on average 30-35 per 100 micron track length. So the role of the gelatin is indeed to provide a three-dimensional substrate to locate the crystals of silver halide and prevent their migration during the chemical development. This is very important to keep the original position, because otherwise this would deteriorate the position resolution. So it cannot absorb a large quantity of waters, which is needed in this during the thermal bath, during the chemical development of the films, and the grains are held fixed like flies on a spider web. So this is very important, to keep the original position. There are specialized companies, and nowadays there are also university or research centers where the production of nuclear emulsion film can be done, and this is done with dedicated machine. There is a dedicated production machine installed underground in the Gran Sasso laboratory in Italy. The production process goes along several steps. So there's first a silver nitrate with sodium bromine or potassium bromine, and they are put in a thermobath with controlled temperature, insertion speed, and the rotation speed. And then there is a second step, which is the wash salt reduction, and then a gel is produced, which has to be poured on a support, a mechanical support frame, which is typically a frame which is optically transparent in such a way that then you can put it on an optical microscope, and it can use either transmission, transmission illumination. And so then this is, once you pour this on a mechanical support, which can be either glass or plastic, then you get what you see here in green. This green is the typical color of this gel when after pouring it on a plastic support. And then you see the film which is on the bottom, so they're made on a plastic support. So the last step is the sensitization, because then you tune the sensitivity, which is the number of grains per unit path length at a given energy deposition in the film, in the sensitive layer itself. So let me go a bit on the history, and so first of all, the discovery of the radioactivity was done by using a photographic film in 1896 by Becquerel, who got the Nobel Prize a few years later. He had placed accidentally an uranium ore on top of a photographic plane. He concluded that this was due to uranium emission different from X-rays. So, and then it was, there's another important milestone, which is Kinoshita observing in 1910 tracks of alpha particles, not just the energy deposition, but the tracks of alpha particles. Then there are important developments done by the Bristol group led by Powell in the 30s and in the 40s in improving and making a higher sensitivity layers. And indeed Powell managed to develop film which are sensitive to electrons. So which shows, of course, a much lower energy deposition compared to alpha particles. So emulsions were originally made of 50 micron thick films with the surface placed parallel to the direction of particles. So one of the issues with these thin plates was to reconstruct also the tracks originated by secondary interactions. So indeed there was quite a significant R&D to develop thicker films, so up to 1 millimeter thick, to contain all the charged products of the interaction, the primary interaction of the particle beam with the nuclear emulsion themselves. So then after the Second World War there was a very active collaboration between academic groups and photographic industries, in particular the Kodak and the Ilford companies. So in the 70s and in the 80s, with the development of electronic detector, emulsion were less and less used. But there was a revolution in the readout technology in the late 80s, and in particular in the 90s there was a fully automated optical microscope for the readout of the films, which really made a revival of the technologies. And nowadays we have extremely fast scanning systems. So this is really a new era of the nuclear emulsion film application. So indeed in the 2000s the Opera experiment was designed and constructed, and this is the largest ever emulsion experiment with an industrial production made by the Fujifilm company. About 110,000 square meter films were built. So the technology was established, and Opera provides its first and unique results in the 2010, and so a new R&D for even faster scanning system were started in 2011. So, and also a new era with nanometric films paves the way for different applications, and it is by itself a breakthrough in the readout technology. So thanks to the ultra-fast scanning system and also to the nanometric accuracy, new enterprise are nowadays possible. So the NewsDM, the SHIP, and the SND experiment. So the one of the major achievements with this detector in the past was the discovery of the pion, which was solving the mystery of the Yukawa meson in 1947, and Powell got the Nobel Prize in 1950, and the committee actually underlined the simplicity of the detector used by Powell. So the emulsions detector in particle physics experiment used to instrument the target region of experimental apparatus in order to study the property of the incoming particle and also of the interaction products. There are basically two technologies. One is the bulk, where the target is fully made of nuclear emulsion, and the emulsions are used as a visualizer detector. This is the oldest fashion of the emulsion technology. The modern way is the emulsion cloud chamber. So the target is made of passive material interleaved in nuclear emulsion films, acting as trackers with micrometric resolution. And so this is a vertex detector with additional performance depending on the structure. So this is the implementation of a bulk emulsion. So you put together one after the other emulsion films, and the particles are typically perpendicular to the emulsion, and most of the volume is a sensitive volume. You have only a little dead volume, which is the mechanical support structure. But normally most of the volume, let's say 90–95% of the volume, is made of sensitive layers. So you really see all what happens at the interaction point, and you use this as a visualizer detector. With emulsion cloud chamber, I mean, you have passive layer which increase by orders of magnitude the mass that you can actually achieve. I mean, if you use 10 times thicker lead plane compared to the emulsion, and then you use lead or tungsten, then you gain a large factor in the density. You get a detector which is instead of being 2 or 3 grams per cubic centimeter is 10–15, so you gain a factor almost 1 order of magnitude in the density. Then you can make a large massive detector in a relatively compact apparatus. Again, you use emulsion films just for as a tracking stations. Then you reconstruct the vertex, but you have enough granularity to see short-lived particles. You put, again, also in this case, as for the bulk, you put the emulsions, the emulsion films with the surface perpendicular to the particles, the incoming particles. Then you have track segments in each film, and then you connect this to get longer trajectories. And you do this all in an automated way. You don't need to do any visual inspection of the vertex. So if you compare the two approaches, the bulk requires provides actually visual inspection at the microscope to distinguish between decays and hadronic interaction, because they show nuclear recoil, nuclear evaporation. So the bulk is normally combined with electronic detectors for the timestamp of the event, for the kinematical measurement and for the muon identification. The emulsion cloud chamber is more compact, is relatively cheap target because it can achieve large masses with a relatively cheap target. It's not fully active, but given the large mass, it can compensate low fluxes and low cross-section, as it is in the case of neutrino physics, for instance. The momentum measurement can be done by exploiting the multiple Coulomb scattering in the passive material, and you can also use the combination, the sandwich between of emulsion and passive layers as an electromagnetic calorimeter for the shower identification and the measurement of shower features. So there is a hybrid setup to provide a timestamp and to restrict the analysis region. So normally you couple these with electronic detectors to get a hybrid setup. And if needed, this will also restrict the analysis region only to the relevant area. So let me give you some other important achievements which were done with the nuclear emulsion technology. So this is not very well known that indeed charm particle was observed already in 1971. The typical discovery time for the charm is assumed to be 1974, with the discovery of a resonance in the E plus E minus annihilation. But indeed, Professor Niu at Nagoya University had observed already charm pairs produced in a cosmic ray interaction, having designed and constructed an emulsion cloud chamber operating on a cargo airplane of the JAL, Japanese Airlines, flying for about 500 hours. And he had also estimated the lifetime of this particle, which is of the same order of magnitude as expected for a charm at hadron. So, and this was 3 years later, but at that time, I mean, the communication between Western scientists and Japanese scientists was not so good, and so this was lacking this information for some time. But it was underlined when Kobayashi received his Nobel Prize in 2008, he was underlining this discovery was actually done by Professor Niu 3 years later than it is normally assumed. Then in the 80s, 1985, there was this direct observation of beauty hadron decays, which was done by the WIA 75 experiment at CERN, and this is the first event observed by Professor Romano. There's a pi minus interacting in the emulsion. There are two beauty, one neutral and one charged beauty, which are produced, beauty hadron. They decay to a charmed hadron, and then the charmed hadron decays in turn. So there is a cascade of beauty to charm and charm secondary decay. So there are basically the production vertex of the beauty, the two decays, and then the two additional decays of the charm. Then other peculiar events were observed in nuclear emulsion technology. The Chorus experiment at CERN in the late 90s observed the diffractive Disabest production, so induced by a neutrino interaction. Neutrino is interacting on a neutron, and it is scattering the neutron off and producing a mu minus because it's a charged current interaction, and a D sub S star. So this D sub S star then decay to D sub S and the photon. The photon is recorded in the electromagnetic calorimeter, and then you have the D sub S decaying to tau and the tau decaying to mu. So this decay channel is rather unique because then it's it shows this double decay of d sub s to tau and the tau to mu, and so it's unique. It's a smoking gun, I mean, for the identification of the d sub s. And then the photon which was recorded in the electronic detector also was part of the overall reconstruction. So it's a very clean event where all this decay chain is seen in the emulsion. And then this is again still the Chorus experiment also observed a very peculiar event, the associated charm production in neutrino charged current interaction. And you have a charged current interaction with the muon coming out, and then together with the muon you have two charm particles, a charm and an anti-charm quark, which then hadronize to two charmed hadrons. And these charmed hadrons are short-lived particles. They decay. One is decaying, the neutral one is decaying after 340 micron, and the other one, the charged one, after 1 millimeter. And this is the full reconstruction of the event, published in 2002, and this was my PhD thesis. So I leave you here with just a few questions to check, I mean, the main messages given in the first module.